Everyone, welcome to the Hertford Astronomy Group and our June meeting. We're going to have a welcome and introduction on screen, which I shall play a little video for.
Good evening, ladies and gentlemen, boys and girls, and welcome to the Hertford Astronomy Group. I hope you have had a very enjoyable time celebrating the Queen's Platinum Jubilee. Unfortunately, my cousin Paddington has been busy, but as his younger brother, Moyniam, I was delighted to come over to the UK and join in the celebrations. You can tell by my accent that I have spent much of my time in the United States. It is my privilege to introduce tonight's meeting. First of all, just a few housekeeping messages. For those of you at the university, in case the fire alarm sounds, the emergency exits are at each side of the screens here at the front. Toilets are located in the waiting area outside this room. For the comfort and enjoyment of everyone in the room, would you just check that your mobile phones are set to silent, please? Thank you. For those of you in Zoomland, please ensure that your microphones are switched to mute, and try to keep away from the space bar on your keyboards, as that can accidentally switch your microphone back on. It is lovely to see so many faces in both locations, and we extend a special welcome to those of you for whom this is your first visit with us. If you get a chance, please come and say hello to any of the committee members who are with us today. The format of the evening is that, after these announcements, we will have a presentation about some of the things that you might be able to see in the night sky. Unfortunately, Martin Weston, who is our vice chairman, isn't feeling too well at present, so Jerry Stone, who is our program secretary, will take us through Martin's presentation. Following Martin's talk, Jerry will introduce tonight's speaker, Martin Hardcastle. Martin's talk will last between 45 to 60 minutes, and there will be an opportunity to ask questions at the end. If you are on Zoom, please submit your questions via the chat facility. After the questions, we will see if we can find Alan, who will give a few closing remarks. Thank you for your attention.
Watch the Jubilee concert. We've seen Brian May on guitar, which, as I pointed out in various emails, means that once again there was an astrophysicist performing at Buckingham Palace. And having mentioned that, you should also be aware that the projection equipment used for that and other events that took place outside the palace, which all did such a fantastic job, was provided by QED Productions, in other words, by Steve Elixir here. So on to this month's presentation about the night sky. Unfortunately, as you've heard, Martin is unwell, not with COVID, I should mention, and he's taking it easy tonight, so I'm presenting this on his behalf. So we all wish him well and hope he'll be back up to full strength very soon. So let's start with an artist's impressions of our galaxy. Being inside it, we can't see these views, of course. As you can see, it is a barred spiral galaxy. And one reason for showing these views is for you to compare them with other images that you'll see later. Now, we've only known for about 100 years that the galaxy actually looks like this. And as for the knowledge of it being a barred spiral, that's fairly recent. The major thing about galaxies is that the spiral arms do not continuously stretch more and more as the galaxy rotates. Many outer stars revolve at a similar rate as ones closer to the center. And it was this fact that led us to deduce that there must be additional mass in the outer sections, mass that we cannot see, which we know as dark matter. That's an evening of discussion all by itself. Another subject of interest is that of gravitational time dilation. The stronger gravity, the more space-time is curved, and the slower time itself proceeds. And so, as it says there, as you get closer to a gravitational source, such as the Earth, the strength of gravity increases, and time runs slower, therefore, for your feet, which are closer to the center of the Earth, than for your head, although the difference fortunately for us, is quite small. Sonda's mother uses, and here's an example showing that it's possible to photograph the International Space Station passing in front of the surface of the sun or the moon without those on board dying in the process. Now we have just 1 week to go until the European Space Agency's Gaia mission will release a wealth of new data about our galaxy. And this chart shows different ways in which Gaia studies the galaxy. But we can go out to collections of galaxies. A new study in Nature Astronomy reports that for the first time, researchers have created simulations that directly recreate the full life cycle of some of the largest collections of galaxies. So not just an individual, but whole chunks of them that are observed in the distant universe from about 11 billion years ago. On the subject of space exploration, the Chinese Space Agency for Human Flights announced that 3 Chinese astronauts, or taikonauts, arrived at the country's space station on Sunday, marking the latest stride in Beijing's aim to become a major space power. Closer to home, you can see some of the best space photography images at the National Maritime Museum at Greenwich in the Astronomy Photographer of the Year exhibition. There are over 100 photographs displayed on brilliant light boxes. The exhibition is open daily until the 7th of August and runs from 10 a.m. to 5 p.m. Adults are £10, concessions £6.50, children just £5, and very well worth seeing. So this example shows NGC 1499, an emission nebula that looks rather like the US state of California. Now in its 13th year, the 2021 competition attracted over 4,500 entries from around the world in 75 countries. Here's a picture taken by Steve of the lunar crater Copernicus, and just to the northeast of it, he is marked the crater Hortensis, and also in that little yellow circle, you might try to find elusive volcanic domes on the surface of the moon, weather and seeing permitting. Here's a couple of pictures by Martin of the Pelican Nebula, a hydrogen-2 region in the constellation of Cygnus, catalogued as IC 5070. This nebula lies right next to the North American Nebula, and it contains an active mix of star formation and evolving gas clouds. There's an ionization front gradually transforming the gas of the Pelican Nebula thanks to light emitted by young energetic stars. Over millions of years, this nebula will no longer resemble a pelican in shape, as the gas and placement of stars will have changed. This is the Crescent Nebula, NGC 688, as it is formerly known, an emission nebula that stretches about 25 light years across and is located about 5,000 light years away from the Earth, again in the Cygnus constellation. Discovered by William Herschel, who we learned about the last meeting. He found it in 1792, and it's the result of a type of star known as a Wolf-Rayet star, which are massive stellar objects that are aging and losing mass at an incredibly high rate. That's certainly the case with this one. The star is shedding its outer layers into space at a rate equivalent to losing the mass of the entire sun, our sun, every 10,000 years, whereas our star has actually lasted for about 5 billion years. And speaking of our sun, there's some spectacular activity on the sun, imaged again by Stephen, using a Lunt 80 solar telescope and using quark chrono as part of the image processing software. And we started off with a view of what our galaxy would look like edge on. This is a real galaxy edge on, the Needle Galaxy, NGC 4565, which is also a barred spiral that spans over 100,000 light years, so similar in size to our own. Located about 40 million light years away. And this bright galaxy is receding from us at some 1,230 kilometers per second. It's known as the Needle Galaxy for its narrow profile, and it's a famous and excellent example of an edge-on spiral galaxy. In fact, some consider it to be a prominent celestial masterpiece that was missed by Charles Messier when he was mapping these objects. If our own galaxy was viewed from this perspective, the Milky Way would appear very much like the Needle Galaxy. The Cygnus Wall is a portion of the North American Nebula, NGC 7000, in the constellation Cygnus. The nebula is about 1,500 light years from Earth, and the Cygnus Wall spans about 20 light years. The wall exhibits the most concentrated star formations in the nebula. This image was made through AstroYard on May the 12th. So thank you, Martin, for putting all this together, but we also have a stop premise from the European Space Agency. This afternoon, they announced that their Comet Interceptor mission to visit a pristine comet or other interstellar object just starting its journey into the inner solar system has been adopted this week. The study phase is complete, and following selection of the spacecraft prime contractor, work will soon begin to build the craft. Right, are there any questions before we go on to the main presentation of the evening? Okay. So this is the final meeting of our 2021-22 program, and we're delighted to be able to be here in our new venue, the Lindop Lecture Theatre at the University of Hertfordshire. And we've only been here since March. Because of COVID, we were actually offered this last year, but we couldn't take up the offer at the time. And it struck me as most appropriate to invite Martin Hardcastle to be our program's final speaker. He is Professor of Astrophysics and Head of the Department of Physics, Astronomy and Mathematics here at the university. His subject, and this really caught my attention when I saw it, is the environmental impact of radio galaxies. That got me guessing, as I'm sure it has for many of you. So I'm delighted to ask you to welcome Martin Hardcastle. And a reminder, watching on Zoom, please submit any questions using the chat facility.
I also need to remember to stay still because I'm apparently on camera over there. I think it's this hybrid meeting, very, very brave of you. I'm delighted to be back in front of an actual live audience. I've done so many talks in the pandemic, and this is the first time I've been back in front of the Astronomical Society since the end of 2019, I guess. I think it was 2019 when I last spoke to this group as well. what I decided to do today was give a talk that's a bit of a sequel to the one that I gave, which was mostly about doing radio surveys back then. And so I'm going to try to tell you something about a topic of research that I've been doing for years now. I started before I moved here, which is trying to understand the environmental impact of radio galaxies. And the first thing I'm going to have to do is explain what the title is about, and then we'll move on to finding out something about what we've actually learned about these things. So here's a structure of my talk. I'm going to start with a brief tour of the universe. We already had actually a little tour of the universe, so I'm going to pick up where that one left off and talk about some of the objects that are going to be important for the rest of the talk. And Jerry's introduction, or Martin Weston's introduction given by Jerry, was perfect in setting the scene for some of the things I'm going to speak about. I'm then going to explain what radio galaxies are, which is fairly key to understanding why they might have an environmental impact, and then spend some time talking about how we have been searching for radio galaxies in the work that we're doing here at Hertfordshire. Then there's a brief part which is how we're actually going out and measuring it, and then look towards the future. So let's start with a brief tour of the universe. If you're an extragalactic astronomer like me, this is what the universe looks like. And so, as you can probably see, this is one of the deep field images. I forget which deep field, but one of the Hubble deep fields. And pretty much everything in there is a galaxy. So the universe is filled with galaxies. And we kind of, extragalactic astronomers don't really care very much about stars. We know they're out there, we're not very interested. Our focus is the galaxies that are kind of building blocks of the large-scale universe. So if you look at, we've already seen some beautiful examples of galaxies. Here are some more. So galaxies come in all shapes and sizes. The most important thing here is just the wide variety of different types of galaxy. You can put these on a diagram and you can try to classify them, famously done by Hubble. We're going to be talking mostly about sort of massive galaxies, which often turn out to be elliptical galaxies, actually very boring in the optical, big fuzzy blobs of stars, not nearly as pretty as some of the things that we see here. But also, but we're talking about the whole galaxy population in all its variety. Galaxies are quite big. We're talking about objects that contain between millions and hundreds of millions of stars. And one of the things that we can do is, as astrophysicists, what we're interested in doing is not just sort of looking at pictures, but also trying to work out what they're made of, what their physical properties are, things like measuring their mass. So if an astrophysicist sees a beautiful picture of a galaxy, they don't say that's pretty, they say, what does it weigh? How old is it? How fast is it moving? How fast is it rotating? How much? All of this kind of stuff. So, and this is going to be important because a concept that I want to bring in is the stellar mass of the galaxy. So I'm going to show a few sort of vaguely plots taken from journal papers to give you ideas of what's going on, but I'll try to explain what they are. So here we're measuring masses of galaxies in terms of stellar mass of galaxies, how many stars, how many, in terms of the mass of the sun. Okay, so you can see we've got, we're going up to 10 to the 11 solar masses. So that's hundreds of billions of stars. Say 100 billion, could say hundreds of billions. So lots of stars. And what this is showing is how many of these different types of galaxies there are. So what we learn from a plot like this is that there are more small galaxies than big galaxies. Well, that's probably not very surprising. But astronomers spend a lot of time trying to quantify, as you measure, how many galaxies there are of different types. So one thing that you find is that there are lots of small galaxies, there are fewer bigger galaxies, so this graph is going down. And then you go up to really big galaxies, they just stop existing. There just aren't any really big galaxies in the universe. So there are no galaxies that we know of that have trillions of solar masses. Those things just don't exist, and that's quite interesting. Maybe they just haven't had time to grow that big yet. But something is going on that's making this plot have the shape it does. Why do we run out to these really massive galaxies? So bear that in mind. While I skip to the next step. So we've talked about galaxies, and again, Jerry helpfully mentioned clusters of galaxies. So galaxies don't just come to spread out uniformly through the universe. You might think that if you go back to some of the deep field images, it's quite difficult to see the concentration of galaxies because you're not just looking at one point in space, you're looking all the way through space, and you see nearby galaxies and distant galaxies together. But models of how the universe evolves and grows predict a complex structure called the cosmic wave, where they predict that the universe is not uniformly filled with galaxies, but it looks like a sponge. So on the left here, this plot is actually a simulation of how you would expect the universe to look, and the colours here tell you about how dense the galaxies will be. All right, so imagine you've taken a cube of the universe and you're just colour coding it by how many galaxies are there in each little bit. And the bright blue is the densest, and the black is low density. And you can see it looks like cut through a bath sponge. There are holes in it, voids, cosmic voids, and there are also regions of quite high density. Now that's not just a simulation. If you go out and do the right sort of galaxy survey, you measure redshifts. Redshifts tell you how far away the galaxies are. So if you've got a redshift and you know where the galaxy is on the sky, you can make a 3D map of where the galaxies are. And this plot on the right here is a slice through one of those 3D plots. So it's showing you true distances. And again, it's color coded, so that the bright and yellow means more galaxies, the black means fewer galaxies. So you can see this sponge-like structure is very, very clear. And this is from data that was current a long time ago. We've known about this for a long time. You can see that here we run out of galaxies, it sort of fades out at the edge because those galaxies are too far away for us to measure their redshifts at the time of that survey. But in the middle, you can see quite clearly that these complicated structures. So galaxies aren't uniformly distributed. There are high density regions and low density regions of galaxies. If you look, so let's zoom into a high density region. This is a cluster called AL 1689, which I just picked because there's some very nice pictures out there on the web. So a cluster of galaxies, a really dense cluster of galaxies looks like this. So you can see all these massive elliptical galaxies, and these will be really, really big galaxies, much more massive probably than the Milky Way. There's lots of them, they're crammed close together in space. You know, they're probably interacting with each other. If you look closely, you may be able to see this, I can see it on my screen. There's a fuzz around these galaxies here, and this is because the galaxies are so close that they're tearing stars off each other, and you get stars that are just floating around in the space between galaxies. So the whole center of this cluster of galaxies is filled with stars that originated in one galaxy or another. You can see it, the odd little spiral galaxy here, blue-looking objects. Most of these things are elliptical and look quite red or orange. If those of you who've got very good eyes can see probably a couple of faint little arcs on this image. Those are gravitational lens arcs. So galaxies behind the cluster that are being lensed by the gravity of the cluster. That's one of the things that allows us to measure the content, the dark matter contents and other things in these galaxies. Not the subject of this talk, but it's just cool that, you know, if you get one of these really deep pictures of a really massive cluster, you're going to see these little arcs. I remember when, you know, there were only one or two of these in existence, and everybody was really excited. But all it takes is some deep images, and you can see them in pretty much every cluster net. So, so there we are. So this would be one of those peaks of density on the plots I was showing on the last slide. This is a really, really dense environment, and if you lived in one of these galaxies, you see a very, very different sort of night sky to the one we see. We live in quite a low density environment, relatively speaking. So our night sky is quite empty of big galaxies. People, you know, or whoever they are living in these galaxies would see a rather different view of the sky. Okay, so environmental impacts. Then this is where I want to tell you something that you possibly don't know, and possibly this is where we move on from sort of basic astronomy and into the realms of high energy astrophysics, which is what I've spent a lot of my life doing. So X-ray telescopes, like this one. This is a satellite telescope called Chandra that I worked on for a long time. I was involved in it before its launch in 1999, so I've been involved in it for a long time. You point a telescope, an X-ray telescope like this at a cluster of galaxies, and what you see is the cluster of galaxies is also full of hot gas. So this image here, a bit hard to see. This is the same image, Abel 1689, but now I've put the purple, or rather people who made the image have put purple on it to indicate where all the hot gas is as seen by Chandra. And you can see that the whole of that cluster of galaxies, we were looking at the central region, we saw these galaxies here and this here, the whole of that cluster is full of this hot gas. And remarkably, in fact, there is more hot gas in the cluster than there is gas in stars. So the majority of the gas that is in that cluster is in the form of this extremely hot gas that's just floating around. It's not ever formed stars as far as we know, though it might have been enriched by stars that formed and exploded in it. It's just sitting there. And it's very, very hot. It's 10 million to 100 million Kelvin, which is a lot. And it's pumping out X-rays like crazy, which is why we can see it. It's really bright in the X-ray, which means that it's cooling. So, if you're just like a light bulb is shining, that means that it's losing energy. If you attach a light bulb to a battery, eventually the battery is going to run down. So you might think, if I've got hot gas in this cluster, and it's putting out X-rays like crazy, it's going to cool down. What will happen if it cools down? Well, it's held up by its own pressure. So as it gets cooler, it should fall into the middle. What's going to happen when it falls into the middle? Well, it's cold gas is falling into the middle. What's in the middle? The galaxies are in the middle. So what should happen is that those galaxies should get bigger and bigger. So for a long time, everybody thought, well, what we expect is that actually this plot that I showed you before, which is how many big galaxies are there, we should see giant galaxies growing right now. Because at the center of these clusters, there's all this hot gas, it's got to cool, it's got nowhere else to go, it must fall onto the galaxies and form stars. But it's not doing that, right? We now know that doesn't happen. So there's a problem. This is called the cooling flow problem. Why is that hot gas, which is obviously cooling, why is it not getting any colder? It doesn't make sense. It's losing energy, but it's staying hot. That can't happen. Energy is conserved. With astrophysicists and stick to that. So this doesn't happen. So this is an interesting problem. Okay, hold that problem in your heads while I tell you about some more constituents of galaxies. I'm going to put all of this together in a little while. So, okay, so the solution to this problem may come from the fact that you've got massive black holes in the center of all galaxies. So this is really, I guess, the last 20 years have seen this realization amongst astronomers that all galaxies have got a central supermassive black hole. Probably the most famous central supermassive black hole is the one in the Milky Way. And the work on this was part of what got the 2020 Physics Nobel Prize. So I've got a movie here which I'm going to explain in a moment. I'll play it again so that I can tell you what you're seeing. But what you're seeing here is this is the center of the Milky Way. It's a composite image. Obviously, we're seeing a big telescope looking right at the center of the Milky Way. And down in the center of the Milky Way, you can measure the movement of stars very precisely. So with these big telescopes in the southern hemisphere, where you can see the galactic center. And what you're seeing in this movie, which I'll play again now, is the motions of a bunch of stars observed over many years. You can see this started in about 1998. So we're fast forwarding quite a bit. I think it runs out about 2015 or 16, depending on which version of the movie I put in the talk. But you can see all these different stars, and they're all moving because they've all got their own orbits. They're moving in the center of the galaxy. But what you notice is they seem to be going round something. They're all describing an orbit round some object. Let's run it one more time. So as you watch these things evolve, you can see that something is bending right. So the orbit of this star, for example, or this star, they're going right round something. Look at this one. It's got an elliptical orbit. It goes wee round and back up again. So something is making those stars move. And this is whatever it is, this thing must be very, very massive, because it's making these big stars and they're zipping around in orbit. So something is pulling those stars really, really strongly. And also it must be invisible, because we're not seeing it in this image. We see the stars, but we don't see the thing that's pulling the stars around. And also it must be very small, because if it was very big, the stars would run into it. We can see the orbits of the star like this, for example, it's going very, very close to whatever that thing is. So putting all of those things together, for many years, people have thought there's very strong evidence for a massive black hole in the centre of the Milky Way, about 3 million times the mass of the Sun. We can't do this in other galaxies in quite the same way, but we can estimate the masses of black holes in other galaxies in various ways. People put all of these together and come to the conclusion that basically the bigger the galaxy is, the bigger the black hole is. So what you've got here is a plot of galaxy mass, so stellar mass and galaxy and estimated black hole mass. And although it's a bit of a mess, this particular plot, for various reasons, you can see that the biggest galaxies have the biggest black holes and the smallest galaxies have the smallest black holes. We're somewhere down towards the bottom end of this, but if you the infographic on the right hand side shows the same picture. You can have little galaxies and they have little black holes. Here's one down the bottom, like us, 3 million sun mass black hole. And as you go up in galaxy mass, you get bigger and bigger black holes. And this seems to be just a feature of galaxies. Galaxies somehow manage to grow these black holes in such a way that they scale with the mass of the galaxy. This black hole picture has recently had a confirmation by some very impressive work on trying to actually image the event horizon of the black hole, which I'm sure you've all heard about before. But this kicked off in about 2019, so it was after the talk I'd given you previously, so I'm going to tell you about it anyway. The 2019 work was a study of an elliptical galaxy quite close to us in a cluster of galaxies called the Virgo cluster. The galaxy is M87, and what they do is put together a network of telescopes spanning the entire world and join them together to get extremely high resolution. And they image the gas around the black hole. They're looking for a shadow of the black hole, because if there is a black hole, then it bends light coming from behind it out of our line of sight, so it looks dark. And this ring-like image is supposedly showing the shadow of the black hole. I say supposedly because there are some other possible interpretations. It's not totally clear how we should understand these images, but I think there's quite a lot of evidence that that these things really do have black holes. So you're not seeing a black hole here because you can't see a black hole, but you're seeing the shadow that it casts on the gas behind it. And recently, the same team have been able to do the same thing in the Milky Way Centre. And so here's another image that looks quite similar, but is actually slightly different. Again, showing that there is a gap in the middle, consistent with the idea there's really a black hole in there. So I think at this point we can safely say there are black holes in galaxies. And so, okay, well, now you might think, what is the connection between black holes and galaxies, which are these tiny, tiny things, and they really are very small compared to the galaxies themselves. Even a supermassive black hole like the one in the middle of 87 is about the same size as the solar system. So it's not big. Right? You can have a billion solar mass black hole, and it's quite a small thing. The mass is very, very concentrated. So how could that have any effect on the large-scale environment? Why am I talking about these two things in the same talk? So the connection comes from what it is that black holes do. They don't just sit there, pulling things around with gravity. When material falls into them, they can do a whole bunch of other things. So here's an artist's impression. Obviously, this is not a real picture. We'd love to be able to take pictures like this. Here's your black hole, and the artist's impression shows a disk of material swirling around it. As material falls into the black hole, we expect it to get hot. it heats up and therefore it radiates, and you can see it. And this gives you phenomena like quasars, where you have an awful lot of radiation coming from the centre of the galaxy. We think that's due to accretion onto the black hole. More importantly for my talk, we also believe that black holes can generate jets, which are very rapid flows of material that come out from very close to the black hole, not out of the black hole, because that can't happen, but out from very close to the black hole. And they move out at high speed, giving rise to phenomena that we can actually observe on large scales. And so the radiation of the jets that the black hole produce can give us, can mean that the black hole has an impact on the galaxy it lives in. To illustrate that jets are a real thing, this is a very high resolution movie of one particular quasar. It goes quite quickly, so I'll just go back. One particular quasar that's emitting a lot of material. You can see that moving out. So the jet, in this case, the quasar has shot out a jet of material that appears to be going faster than light. That's an illusion, but it's going very, very fast over very small scales. So you see we've got scales of 100 light years, and this thing zoomed out over 18 years. You can see this material coming out from the centre of this galaxy and propagating out into the galaxy itself at very high speeds. So it's that we're going to be talking about in the rest of the talk. It's that connection between the central black hole and the rest of the galaxy, which is where radio galaxies come in. So before we go on to radio galaxies, I need to explain to you why I'm talking about radio. So for some people in the audience, this will be fairly obvious, for some not so much. Radio telescopes are telescopes that operate at very long wavelengths. So that's sort of tens of meters down to millimeter. Most of the telescopes I've been working with recently operate at a wavelength of about 2 meters, which is very conveniently about the size of a person. So you're measuring waves that are about the same size as you are. A trick that you can do with radio telescopes, and you can go into a lot more detail here, subject for another talk, is that you can join many antennas together to make an image that's high resolution, and you need to because the waves are so large that you need a very big telescope to make a good image. So something like this, which is a very large array in Mexico, is made up of many antennas like this. This is a 25-meter radio dish, person to scale and cast to scale here, so you can see the big thing, and then you make lots of those, join them all together, and you can make these very high resolution images. And the only real bit of astrophysics in this talk is I'm just going to explain, because I usually get asked, why are these galaxies making radio waves? It turns out that there are charged particles moving about in the galaxies. They move about in magnetic fields, and that gives rise to a sort of radiation called synchrotron radiation, which happens to come out very brightly in the radio. So if that answers a question that I would otherwise be asked, that's the purpose of this slide. Just for the rest of you, just take it as read that the energetic particles in these things make radio waves, and that's how we get to see them. Okay, so what's a radio galaxy? Well, a radio galaxy is a galaxy that has a supermassive black hole at the centre, and it has these jets that I talked about that you see coming out of the black hole on small scales, but they don't stop on small scales, they go out to very large scales. So this is a galaxy called Hercules A, and the image we're seeing here, by the way, is a composite radio and optical image. So what you're seeing, the normal colours here are an HST image. So here's an elliptical galaxy, here's some other galaxies. And then on top of this is an image made with a very large array, which is showing you this kind of pinky purple structure. This is radio emission, and you can see it's coming from scales much larger than the host galaxy. So this quasi-elliptical galaxy, which would be a massive galaxy, maybe the size of the Milky Way, and we've got these very large structures that are coming out on scales much larger than the galaxy. So out to millions of light years or more, we're generating these jets. Now this is what we care about, because we want to understand how can the radio galaxy, how can the central black hole influence the environment around it. Well, this is how, because the black hole is generating these structures that go out to millions of light years. Okay, and so you can see You can see in this case the jets. You can see these things and loads, which are big sort of bubbles inflated by the jets. I'll show you some modelling of this in a minute. And you can also see, although we don't show it in this picture, that this is a cluster of galaxies again. And so there's hot gas out here filling the space between the galaxies. Another question I'm usually asked is, how are those jets coming out? You know, how do they get out from the black hole? And again, I'm just going to give you a hand-waving answer. It's in a sentence, the idea is that we've got a rotating black hole, we've got magnetic fields, and as the black hole rotates, it twists up the magnetic fields. And that causes, so this is a picture of magnetic field being twisted up from an actual simulation, not one of mine. I just put it up the web because it's pretty. It shows that the field is being twisted up, and as the field is twisted up, energy builds up, and that pushes the jets out from close to the black hole. And this used to be speculation, which is really well supported by simulations. It's quite hard to observe. We think this is how it works. So the centre of the black hole make the jets because of actual black hole physics, which is kind of interesting. Again, not the subject of this talk. How do we make the load? So this is one of my simulations, and this is just showing what happens when you take some very fast jets and you let them run out into an environment like you would find in a cluster of galaxies. I'll let this run this loop, so I'll let it run several times. So what we're seeing in the sort of orangey colours, this is our best idea of what the radio emission would look like, and in blue colours we're seeing essentially what the X-rays would look like. So what the hot gas is doing. And you can see that the jets, as the jets go out, they're very light, so they blow these bubbles. The bubbles are the loads, and they move out with time because the jets are on all the time, they're pushing things out all the time, so the loads grow, they get bigger with time. We can't see this happening because those structures are so big, but we can model it in our simulations and we can see how we expect them to evolve. So it sort of makes sense that we get the structures that we do, and we can make something that looks pretty like a radio galaxy. And we can also look then at the radio galaxy's impact on its environment. And so this is a picture that encapsulates all of this in one go. We've got a cluster of galaxies here again. So the background image is an optical image. The red colour is a radio galaxy made with a very large array. And the blue here is X-ray emission taken with Chandra. And you can see that remarkably similar to the simulations. So the radio galaxy is making holes in this blue X-ray emission, punching holes, inflating these cavities. It's stretching out the blue X-ray emission, so it's elongated along the axis of the jets. That gas is being pushed out by the jets and the loads, and it's kind of stirring it up. So you see all this complicated structure in the hot gas. So rather than being this, if you just let that gas sit there in the central cluster of galaxy, you get this smooth, rapidly cooling, boring ball of hot gas. But when you put the radio galaxy in, it has all sorts of effects on the X-ray emitting material, and in particular, it's heating it up. Right, so a powerful radio galaxy like Cygnus A here can completely offset the effects of all that cooling. It can stop the gas from cooling, and it can therefore stop galaxies from growing too big. So a take-home message is that right now is that astronomers think that radio galaxies are actually responsible for there not being really massive galaxies in the universe. This phenomenon that starts in the centre with jets from the black hole actually determines why there aren't really massive galaxies, which is quite surprising. And it's very, very different scales involved here. Okay, just to prove this isn't a one-off, here are some more pictures of radio galaxy environmental impact taken with Chandra. This is one of mine from a few years ago, showing Chandra observations of the very nearest radio galaxy, Centaurus A, and you can see that these purple things are the radio loads, and you can see the rims of X-ray emitting gas around the radio loads as the radio loads push this gas out of the way. It's expanding very fast. In this case, you get very thin rims of gas trapped up against the radio loads. This thing is very, very close. It's only 10 million light years away. So it's basically the closest radio galaxy there is in our backyard. This is a very nice Southern Hemisphere object, of course. Slightly further away, just show the X-ray images because this is so beautiful. This is the nearest rich cluster of galaxies, the Perseus cluster, and in the centre of that is a thing called entity 1275, which is where many, many generations of bubbles have been blown. You can see all the structure in the X-ray gas, and we think that's all due to a succession of radio galaxies going off in the centre, each one blowing a little bubble. So this is really happening all over the place. And in individual cases, we can study it really well by using X-ray telescopes and radio telescopes together. The key question is, it's nice to tell a story and to say, well, it works in this galaxy and it works in this galaxy, but does it work overall? Does it work for all the galaxies? Is it really true that the radio galaxies as a population can stop all the cooling of all the gas in the universe and stop those galaxies growing bigger? How much energy are they really putting into the hot gas and where does it end up? Okay, so to answer that question, we move to part 3 of the talk, which is radio surveys. How are we going to find these radio galaxies? So what we want to do is find all the radio galaxies that we can. And those of you who remember my talk from a few years ago, there may not be anybody here, there won't be a test, will remember that up till now, we haven't been able to do surveys of the radio sky that really allowed us to find all the radio galaxies. So the Very Large Array, which I showed you a picture of, is a wonderful instrument, but it's actually not very good for this purpose for technical reasons I won't go into. So we needed to build new types of radio telescope, and the one I'm going to talk about for the rest of the talk is this thing called LOFAR, which is here you'll see in the very centre of the array, of the LOFAR array. The LOFAR array is actually much larger. I think I haven't got a slide on that. So it spreads across the whole of Western Europe, in fact, with a core in the Netherlands. So this is the core of the core. So you can see a bunch of stations here, which are the LOFAR stations in the core, but then it spreads over the whole rest of the Netherlands. It's actually just the Dutch telescope, so I'm going to be using for the rest of the talk. We're doing a survey of the whole northern sky. We can't do the southern sky because we can't point this telescope because unlike the BMA, these are not dishes, these are just flat panels with radio antennas in. So we can only look up in the north. We're kind of trying to do the whole of the northern sky, and that will find all the radio galaxies there are in the northern sky. And we're sort of getting there. So this is a picture showing the northern sky, and the green is bits that we've done. So there's quite a bit we haven't done down towards the celestial equator, a little bit we haven't done, and quite a lot we haven't done where the Milky Way is, because the Milky Way is difficult. It's quite bright in radio for other reasons. There are lots of supernova remnants and things, so we're not going there yet. But for extragalactic work, what we've done right now is quite good. So we've got good coverage. The final project needs 3,000 separate fields to be observed, and we've got about half of those here actually. So you can't see this. It looks better than that, but it's actually about half finished right now. So we're getting there. But half of the sky done very well is still pretty useful. In February 2019, and I guess this might have been about the time I was talking to you previously, we had a first data release of this survey, and we covered 400 square degrees of sky, and we had some very pretty images just from that tiny region. We had a special issue of astronomy and astrophysics and a lot of media attention everywhere else, but Britain, especially with the Brexit at the time, and nobody cared about the radio galaxies, but there you are. Priorities people, say. The bulk of the imaging processing for this survey was done right here in Hatfield, and you can go on our website, lofar-survey.org, and see many more pretty pictures. Since then, we've been doing another data release, and this is data release 2. And I'm just kind of flying through the radio sky for you in this movie. So there's no way of representing how good this data set is. It's just so big. There is so much. So this is just like a fly through the radio sky, and you can see a bunch of things. You might think these little dots are stars, but they're not. Each one is a galaxy. Basically, there are no stars in this survey. Everything is a galaxy. Stars are not generally very strong radio sources. Starts up with a little spiral galaxy there. I think that's a famous one, but I can't remember which one it is. You can see, and you can probably see whizzing by a bunch of radio galaxies. You can see them because they've got this double structure that's generated by the jets. There's a bunch of other strange things, lots of little dots. So there's a lot in there. There's a radio galaxy. There's a lot of stuff in here. That's a tiny fly through a tiny portion of this survey. It just kind of shows the sort of thing that you can see if you just look at it. In total, we have about nearly 6,000 square degrees of sky, which is a lot, and 4.5 million radio sources, which is the largest radio survey ever by some way, 10 times deeper than the other survey. And processing this involved 8 petabytes of raw data being processed in several stages. Again, most of it ended up not the first stage data, because that's just too big to get here, but the second stage data ended up in Hatfield for the final processing. So, are there radio galaxies in here? Well, yes, of course, there are radio galaxies in here. So again, here's another one of our press images showing how many, the sorts of radio galaxy structures you can see. There's loads of these double radio galaxies. These are the things that we care about. We want to find all of these, count them, work out how powerful they are to try to answer the question, could they really be doing the job we think we want them to do? So we have lots of radio galaxies, but that's only half the problem. If you find a radio galaxy in a radio survey, you know that it's a radio galaxy, but you don't know what radio galaxy it is, you don't know how far away it is. And if you don't know how far away it is, you don't know how bright it is, you don't know how bright it is, you can't do any astrophysics. The first thing that we need to ask, here's a radio image, where do we get our numbers from? You can't get any numbers unless you know which actual optical galaxy it belongs to. So this is the optical identification problem. This slide shows the colors here are just radio images. They don't actually match up. So this is the sort of thing we see if we just look at radio. When we look at radio and optical together, we often see, here's an example. Here's a galaxy that has got a radio galaxy that's got a nice optical galaxy sitting in the middle. So okay, we say, well, that radio structure there belongs to this galaxy here. Have we got a redshift for that galaxy? Yes, we have. Now we know what that radio source actually is doing. We can do some astrophysics. There's another one with a nice galaxy in the middle. Some of these things are not so easy. I think this one is an example where it's a little hard to see where the galaxy in the middle is. Maybe it's just too distant to see. So there is a problem, which is that we've got to go off and try to find all the optical IDs, all the optical galaxies that go with the radio sources. We've got some very nice data to do this with, as it turns out, because these kind people doing the DESI legacy survey happen to have got just the same amount of sky that we have. So in fact, they're doing slightly better. So their sky coverage is this. The blue here, and ours is, sorry, there's the yellow, ours is the blue. You can see that actually we've got a very nice overlap with their survey, and it's beautiful data. This is just a random press release picture they put out, but it shows the quality of their data. So we can, at least we can actually go and look and find out where the galaxies are. This quote here sort of summarizes the problem. If you just have a radio source, it's useless. You don't know what it is. You've got to match it up with an optical galaxy, and we've got the surveys to do it. So we've got 4.5 million radio sources, and we've got hundreds and hundreds of millions of optical galaxies. All you've got to do is match them up, right? And then you're done. What do? You go to the internet. Actually, you don't just go to the internet. So that would be too big a problem even for the internet. So the first thing you do is you match up all the easy ones with computers, and you say, okay, if the radio source is really compact and it's sitting right on top of an optical galaxy, let's not ask somebody to do that job. Let's just assume that those things match up, and you do it with algorithms. But we have been working on a big citizen science project to try to get all of these things matched up so we can do the science. So only about 200,000 of the 4.5 million sources went to the citizen science project. We've had 950,000 classifications so far in our numbers. It's not finished yet. So if anybody's really keen to see more of these things, here's where to go. Local galaxies moved on in now, or if it's from the survey site, or come and see me afterwards, because we could use a few more clicks to be perfectly honest with you. 10,647 distinct volunteers. So, there's lots of people going in there getting involved. That project is going on. It's going very well. We're getting lots of results out of it. And I'm going to tell you not about results from the full survey because we haven't got them quite yet, but results from work we did earlier on in the pilot survey, and then tell you where we're going to go next. So, what do we do with all of this to try to answer this question about environmental impact? So going back to the sort of astrophysics questions, there are things we can measure. If we've got a redshift, there are things we can measure and things we can't measure, and things that we'd like to know. So here's my sort of astrophysicist view of a radio galaxy here. We can quite easily, if we have a redshift, we can measure things like the galaxy mass. We can measure the black hole mass. We might be able to measure the environment properties, like how much hot gas is there with an X-ray telescope. What does that weigh? We can measure the radioluminosity. How bright is it? How bright is it shining? Because we can see how bright it appears to be. We know how far away it is. So we put those together. We know how brightly it's shining. We know how big it is because we know how far away it is, and we know what size it appears to be on the sky. So we can measure all of those things. The trouble is that what we'd like to do is measure things like how much power is going up the jet. So this jet power, which is given a simple Q for some reason, is telling you how much energy is that black hole putting out into the environment. You'd really like to be able to measure that, but you can't. Right? You need to kind of go in there and you ideally sort of stick a power meter in somehow and measure it. And you can't do that directly. You also don't know how old the source is. Right? A simple question. We know it's big, so it must have some age. It didn't start that side. It's growing. So it must be old, but how old is it? That's quite difficult to know. These two questions, of course, are tied together. The more powerful the jet is, the faster it's going to push through. So now what you really want to know in order to answer these questions about environmental impact is, you take all the radio galaxies and work out all their jet power simultaneously, and that tells you how much power they're generating right now to offset that cooling of hot gas. That's difficult because we can't directly measure that. So what we're doing is we're going through the statistics of these surveys and trying to get at this kind of indirectly, not one galaxy at a time, but all at a time. Now, the first important thing is a piece of information that I think we really didn't know before we started, which is that every massive galaxy is actually doing this at some level. Now, that's really important. It's not just the spectacular, pretty ones we knew about. They're all these massive galaxies are making these jets, and they're all therefore having an effect on their environment. This is summed up by these plots, but rather than trying to go into these in detail, what I'll say is that basically this is just saying, as you go to, this is saying, what's the fraction of galaxies hosting this sort of radio activity, dependent on their stellar mass. And you can see that once you get up to the most massive galaxies, say above 10 to the 11 to 10 to the 11 and a half stellar masses, that fraction is getting up to 100%. So they're really doing this all the time, and that was one of our key discoveries from the first data release. Now, what I wanted to do was find all the radio galaxies and separate out all the things that aren't radio galaxies. The other problem we have is that there are a bunch of radio sources that are not radio galaxies. They are galaxies that emit radio, but they're the wrong sort of radio. They're just ordinary boring stuff in the galaxies like the Milky Way. We don't care about those, so we need to take them out. And a lot of the work I was doing in 2019 was trying to devise ways of taking them out, which I won't bore you with, except to say that we had to throw an awful lot of things away. So we started with about 300,000 candidate sources, and we ended up with about 23,000 things. We thought that those are definitely radio sources, radio galaxies. We don't know what the rest are. They're most likely star-forming galaxies, but we're just trying to pick out the things we knew for sure were radio galaxies. About 7,000 of those were actually resolved with low farming. You could make pretty pictures showing the double lobes. 16,000 were unresolved, so they look like point sources, so that's rather boring. And then we went out to quite high redshift, the distant universe. But the place where we should concentrate really is the nearby universe, because we understand it better. So what we're trying to do is actually say what is the effect of these things at the nearby universe. We throw away all this really distant stuff. So The key thing that we did here that I think is new and that sort of helps us to answer this question is that we tried to work out ways of inferring the things we don't know from the things we do know. So we can measure things like the size and the radio luminosity, and we can make plots like this which show how big are the sources, how bright are the sources, and put them on these plots. And we can use models that tell us how radio galaxies evolve on that sort of a diagram. So it's a bit like an HR diagram for stars. Radio galaxies will move around on it during their life. These tracks show the movement of various radio galaxies. So by localizing the galaxies on this sort of plot, we can try to work out how powerful they are, how old they are, and things like that we don't know directly. This thing here just shows an example of the sort of diagram we can draw with. We can try to turn position on this diagram into the thing we care about, which is jet power. So the sources that turn out to be that are the biggest and brightest turn out to be the most powerful. That sort of makes sense. The more powerful sources, the brighter it's going to shine, and the bigger it's going to grow. But that's the sort of the details of how that works. You have to use quite detailed models to work through. We have a big problem. We can't measure all of the sizes of all of these things because a lot of them look like point sources. So we have to take some educated guesses about where we should put them on the plot. Although it's an important detail, it's a detail. And the headline result, which I know this is not a very aesthetically appealing result, it's more like accountancy than anything else. We added up all of the power of all of the radio galaxies that we could find in the local universe. And we also added up all of the cooling power, that is all of the X-rays that are coming out of all of the clusters in the local universe. So balance sheet, the question is, we know this X-ray cooling is happening, we know that radiation is coming out. We want to balance that against the radiation, against the power that's being put in by the radio galaxies. Are they the same? I mean, and when I tried to do this calculation, I would have settled for, one is 10 times bigger than the other. That would have the right order of magnitude would have done. The answer is, one of the radio galaxies are putting in 7 times 10 to the 31 watts per cubic megaparsec. These are funny units, I'll come back to in a minute, but the clusters are losing 4 times 10 to the 31 watts per cubic megaparsec. So, now for an astrophysicist, that's really good at balancing the books. Those numbers are very really the same. It's incredible degree of agreement. So what that tells you is that the radio galaxies, the heating that's put in by the radio galaxies, the whole population is enough to stop all of the gas in all of the clusters in the local universe from cooling. So we didn't know that before, now we do. Radio heating is approximately the same as cluster cooling. This watts per cubic megaparsec, 7 times 10 to the 31 watts per cubic megaparsec. To put this in perspective, this is a tiny heating rate. If you take when I thought about this, I thought about 50-watt light bulbs. There aren't any 50-watt light bulbs anymore, but bear with me. You're all old enough to remember 50-watt light bulbs. So the 50-watt light bulb, put that in the middle of the solar system. And go out to the edge of the solar system, out to the orbit of Neptune, let's say. So 150-watt light bulb per solar system, that's the same as that heating rate. It's tiny because clusters are so rare and radio galaxies are so rare and space is so empty. But that comparatively tiny amount of energy is enough to stop all these massive galaxies from forming from the universe looking completely different from the way it looks. So, okay, what's next? Kind of solve that problem. The problem we solved is can this actually work? And the answer is yes. Right. So now the question is, how does it work in detail? How can we test it further? A prediction would be, for example, that we need more radio galaxies where there's more cooling. Because if it turns out the radio galaxies are in the wrong place, that's no good. So you want to do more sophisticated things, which you need more radio galaxies. So we're going to do the same sort of thing with the second low power data release. That's 10 times the size, much more we can do. And we're already starting to write up some papers, and this is there's too much words, too many words on this, but basically we're already starting to pick out the radio galaxies from the next the much larger sample, more than 10 times the size, where we'll be able to ask these questions in more detail. What's actually going on in different environments? A really important thing is, and again, this is a project led from Hatfield, not by me, by my colleague Dan Smith, is to get redshifts for more of these things, because we can't really do anything very good unless we know distances to all the radio galaxies. To do that, we've got dedicated observations on a thing called WEAVE, which is the optical instrument on the William Herschel telescope, which is going to measure redshifts for all the optical host galaxies we can find. So that's another impetus to get to all those optical galaxies. We're going to be able to take redshifts of all of them, and that will really help us to narrow down what they're doing, where they are. And that should be starting to take data this year, I hope. It's been long delayed because of the pandemic, and because they dropped it on the way to the telescope and a whole bunch of other calamities, but it really should start to get up there sometime soon. And the question that I'm often asked by people with technical bent is, are we all going to be saved by machine learning? Are the computers just going to be able to do this for us? And the answer is maybe. It's too late, because we've already done most of the work. We've already got to 1 million clicks from human volunteers. It would be a great shame if we now have to tell them you don't have to do this work. But actually, there's some very interesting stuff going on in machine learning to try to do this kind of image analysis with computers. And that's going to be necessary when the next generation of radio telescopes come along with even more data. Can't do it yet, but we can do some of what the human volunteers do, and this is quite interesting. One thing that we really want to be able to do is get better radio images with more resolution, so we can see the sources better. I told you that most of the radio galaxies that we found, we couldn't make proper pictures of because they just appeared like little blobs. So if you get better resolution, you can do that even better. LOFAR has these long baselines that go all the way out across Western Europe. We've got a station here in this country, one in Ireland. There are some in the Baltic states and Sweden. There's one in Italy coming soon. So it's with all of those stations, it can make very high resolution images. We're just learning to process that data. It's very computationally difficult, and we're doing some work on that here as well. But if we can do that, then we can make much better images, and that lets us understand the thing much better. It also helps us to find the optical host galaxies much better. What's coming down the track next for radio astronomy is the Square Kilometre Array, which I'm sure you've all heard about. And this is going to be starting early science in a couple of years now. Full operations probably by the end of the decade if all goes well and they don't run out of money. And this is going to be a huge advance in the capabilities of radio telescopes, and a massive data challenge. The data that's going to be produced is much, much larger volumes than anything that's gone before. Just actually dealing with the data, getting it from place to place, allowing the users to analyze it is a really big thing. And before we can start doing the astrophysics, we have to solve that problem. So we're working on that here at UH as well. This slide, I left this in, but this is a bit of a sad slide. The new X-ray work would be really helpful. So we've got these two old X-ray telescopes in orbit, Chandra from 1999, Exner and Newton from 2000. They're both still working, but they're not going to last forever. And you really want to be able to get X-ray observations to measure that hot gas directly and say, what's the environment doing? That's a missing piece of the puzzle. We can't do that right now for all our radio galaxies or anything like that. So there's a satellite called Rosita. It's in orbit. It's a Russian-German collaboration. So when Russia invaded Ukraine, they turned it off. The Germans said we're not playing anymore. Quite understandably. So beautiful pieces of equipment that's not working right now. I understand the Russians are saying we're going to turn it back on anyway, but that's not going to help, because nobody knows what's going to happen to the data once the Russians have taken it. So this thing, Rosita, which we were going to be using to match up with our LOFAR surveys, is not currently in existence. Athena, which is the next big European, pan-European radio X-ray telescope, is currently having a bit of a budget crisis and may not survive, despite being in the ESA roadmap. And it'd be a great shame because there's some really good stuff that we could do with Athena measurements of radio galaxies. But we live in hope that some of these things will start working there. And then the final piece of the puzzle, I think, is new modelling. So we've got to model the whole range of things that we might observe. Here's some work from a UH PhD student modelling the effects of rather than just having the jets go into the medium and go in straight lines. What happens if the jets are moving? What happens if the base of the jets are moving, as we expect in some black hole models? And you can observe that a lot of, some of the detailed structures that we see in radio images of these things start to appear in this kind of simulation. So what we can do, in parallel with getting the much better radio data we're going to get, we can get much better models of how these things work and understand them far better, and put that together to get a better interpretation. And that's going to be absolutely crucial, because we even with the LOFAR data, we're already seeing all sorts of things we don't properly understand. And the better the models are, the better we're going to be able to do. All right, so final slide, and I think not before time, I'm sure you will say. Just to summarise then, what are the take-home messages? We've got all this hot gas in the universe, and it's a very long-standing problem. Why is it still hot? Why hasn't it cooled down? It's radiating. Why is it not cooling? It's not a new idea that radio galaxies can do it. We kind of see this happening. The energy supplied by the jets of these radio galaxies goes out to very large scale, where it can heat the gas effectively and continuously and keep it hot. But what we've done, the new result that I've shown you, is that we can prove this works as a population by taking all the radio galaxies we can find and all the clusters that we know about and adding up the power provided by the radio galaxies and showing it's equal to the rate of cooling. We couldn't have done this without these new radio surveys that allow us to find all the radio galaxies that are out there. The future is only going to get better from this point of view, because we can improve these calculations. We're going to get much more data, better telescopes, and we can also take this back to the early universe. We can't do this work yet, and understand how clusters have been shaped by the radio galaxy, the radio galaxies they host, out to the very earliest times of cluster formation, which will be very exciting. And I'll leave it there. So thank you very much for listening. I'm happy to take some questions.
Thank you very much, Martin. Are there any questions here in the room, first of all? So shy. Do we have any on Zoom? Right, which leaves me an opportunity. Yeah. Something which I've thought of, because earlier on, one of the things that you mentioned was about, so we're looking for two values, Q and P. And it struck me, we can see younger galaxies if we look further away, because we're looking further back in time.
Yeah.
So what is the age of the youngest galaxies, roughly, that we can determine?
So the youngest galaxies that we can see if we look right back into the early universe are very young. Yeah, there's evidence for very for ages. You don't see galaxies until stars are formed. So something that's just a collection of gas in the very early universe, no stars, you can't see it, so you don't. So we kind of date it from when did the first stars form. You can't see the first stars forming, but you can see the second generation of stars forming. And so we're talking about things hundreds of millions of years old, the kind of youngest galaxies that you see. Now, so I know where you're going with this, of course. They can't possibly have the very large radio structures in them because they wouldn't have had time to grow. Problem is, there are other reasons why in the very early universe it's actually quite difficult to be a radio galaxy. So they are the gas is very clumpy. It's a repeat the progress of the jets. The radiation field is very intense, and that tends to make them lose energy very rapidly through different loss processes. So the very, very early universe is not a good place to be doing this. Where we quite like to do it is the peak epoch of galaxy growth, which is about region 2, where we can't go yet. The galaxies there are quite old, but there's an awful lot of stuff going on. That would be a very nice place to go. The thing is that these things are not always on. The jets aren't always on, because if the jets were on from when the galaxies started to now, everything would be 15 billion years old, and the sky would be absolutely full of giant radio galaxies. It's not. So they turn on and off. They have episodes where they're not there, and episodes where they are there, presumably because of feeding of the black hole being different at different times. Yeah. So when I say what's the age, I mean what's the age of the current galaxy we're seeing, which could be very much younger than the age of the galaxy. So the radio structure we're seeing is much younger than the galaxy it is, because the black holes just started up to do something new. In fact, we know of kind of radio galaxies that are only hundreds of years old, that just started, or maybe even tens of years old, that just started up in quite old galaxies in the local universe. So more complicated than that.
We have a question from Keith Bennett. Hi, Martin. Apart from those you've mentioned, what do you think are the main unanswered questions about AGN, and what you'd like to be answered over the next few years?
Well, that opens a big field for me. There's AGN in general, of course, encompasses all of the activity from all the different different things that the black hole can do. So it includes things like quasar activity. And I think a relevant question here, which I haven't talked about at all, is what do quasars do? So when you have all of this light coming out, you've got this quasar, these very powerful light sources, and most of the energy in most quasars is coming out entirely as radiation and not as jets. So we don't really understand the impacts of those things on their galaxies. Some people say, without very much evidence, I think, that they are very involved in this galaxy evolution process. Other people disagree. So that's a big unresolved question. The thing I always say about this is that if you can see the photons, so if you're seeing a quasar, that means the light is coming directly from that distant galaxy to you, which means it's not stopping on the way, not doing anything to the galaxy because it's left the galaxy. But there's a lot to learn about that. A very interesting question for me is what sets that balance between how much the radiation that's coming out from a sort of classical quasar like AGN and the jet power. So what determines those different numbers? They certainly aren't always the same. There are objects that have basically no radiation, or jets, and objects that have lots of radiation, and pretty much no jets. We know black holes are supposed to have no hair, so there's not very much we can do about black hole properties. They might be spinning or not spinning. That's about it. So what sets those different behaviours? That's quite crucial. We don't understand a lot of the detailed physics of how the radiation comes out of the radio quiet AGN anyway. But the ones that are just very bright and optical, that's poorly understood. So there's a vast field of ignorance in this area. Absolutely, everything you start thinking about it. What's going to be solved in the next few decades? I think I'll just give one, because otherwise this is going to be a very long answer. Something that I think we will learn a lot about for ordinary AGN is time variability through things like the LSST, and now the latency server of space and time, which is going to be taking lots and lots of optical images with a very short cadence. So you'll be able to see how the radiating output of these things changes with time. We can't do so much about this in the radio galaxies. We can, because they are very large structures, they evolve very slowly. But we can look at the variation of radiative power being put out by the AGN with time. And I think we're going to learn an awful lot about how AGN are fueled and how they actually produce that radiation by studying, you won't just have one light curve or one AGN. Again, you'll have the whole population, you'll have hundreds of thousands of objects, and by studying that, I think we're bound to find out something about how how that particular aspect of it works, so how the fueling works, and how the radiation is generated.
Any other Steve? Any more? Yes.
Yeah, I'll, it's probably doesn't make any sense, but looking at the slide just here, the top right shows a fascinating picture of the cluster of galaxies with the very hot gas.
Yes.
And then the radio coming off the end. It looks like the radio waves are sort of disappearing off into space out of the cluster of galaxies, which, if they were, would that not sort of they'd be disappearing into space, and therefore they wouldn't be keeping the temperature. They wouldn't keep the temperature up.
That's a brilliant point. Actually, yes, that's a really important consideration. And it's one. I mean, it's actually there in the paper we wrote about this. So it's been known for a while again. You're quite right. You know, where is the energy going right now in this system? It's going off into very large scales. Whereas the cooling happening right now, it's happening in the middle. Yeah. Right, the cooling, you can see the cooling is happening most there because it's the X-rays are brightest there. There is material further out that you can't see in this image, of course, but that's what's being heated right now, and it doesn't need to be. So a lot of the energy that's being put in is not going to the right place in a system like this. Now, in a system like this, it also doesn't matter because this Cygnus A here is so powerful that actually it turned off cooling, you know, when it was yay big. You know, when it was right in the centre, it's already done the work it needs to do. But there's a real question about the sort of analysis that I'm trying to do, which is, you know, I'm saying I know how much energy that they're putting into the population, but I don't know where they're putting it and whether it's the right place, because I don't have that information for those objects. So no, I think there are some ways around that. One thing that we notice, I'll just go back to another of these pretty pictures to answer this one. One of the things that we notice in the really rich environment, to go quite there we go, really rich environments like Perseus cluster, is that the radio galaxies seem to turn on and off all the time. When they turn on and off all the time, of course, they start from zero size, so they're always heating the centre. They just blow these, you know, a succession of little bubbles. Now, the question is, how do they know to do that? Because it's not obvious. But there's some evidence that this sort of structured system works with a kind of cosmic thermostat. So the hot gas starts to cool. When it starts to cool, some of it falls in. When it starts to fall in, some of it accretes. That turns on the jets. That heats up the gas. That stops the material falling in. So the AGN turns off. So then you get the bubbles blowing out, rising out gently. Some more heating. Then it starts cooling again, and the cycle goes round. So you've got a feedback loop that's actually, in this case, organises for the radio galaxy to stay in the middle, doing the work it needs to do in the middle. That's clearly not happening with Cygnus A, but as I say, maybe this is more the norm, and this is beautiful but unnecessary in the grand scheme of things. But this is a question we don't really know. We don't know the details of how this works, or even. And this is what I want to be able to do, actually, to be able to say, okay, we've got this amount of energy being put in by these radio galaxies, but what sort of environments are they living in? Where are they in those environments? Is that heating really where it needs to be? That we can do with much larger samples if we can kind of constrain the environments of those galaxies, so that we know what their cooling rate would be. Of course, we do it. In fact, we can't make these X-ray observations for every single galaxy, you know, every single 4.5 million sources, because the existing telescopes just aren't good enough to do it. So we've got to find other ways of inferring that environmental information. But that question is one of the big outstanding questions. Yes, it adds up, but is it actually doing what it needs to do?
Any others? Okay, no more online. Okay. In that case, I think what else can we do but thank Martin for his superb presentation. This is obviously, as with many things with astronomy, it's not something where after a while we're suddenly going to say, right, this is it, we've solved everything. This is job satisfaction for quite a while.
I'm expected to take me to the time.
Yeah.
After that.
So we look forward to an update at some time in the future as well. But for now, thank you very much indeed.
Thank you, Jerry. Well, we couldn't find Alan, so I'll do his bit. First of all, let me say thanks to Martin on behalf of all the Zoom folk and university attendees. It was a fascinating talk full of very interesting information about quite a complex subject and delivered with great enthusiasm. I am sure that you have taken our knowledge and understanding quite a few steps forward. I would also like to thank Martin Weston for his contribution to the meeting with a presentation that Jerry delivered on his behalf. There were some stunning images there, and Martin's talk enlightens us all as to some more of the mysteries to be explored in space. Just before we go, there are a couple of announcements that we need to share with you. Firstly, on Sunday, the 10th of July, we have been invited to attend the Wheat Hampstead Village Day. We can set up a stand to promote our club like we did a couple of years ago. There will be lots of people there, and we can show them some of our telescopes, and maybe even show them some images of the sun. There will be lots of other stands there with a wide variety of interesting themes. If it was like last time, then there will be a carnival procession. Think of it as a slightly smaller version of the Jubilee one with many interesting participants. Secondly, we have once again been invited to put on a display in the Garden City. This will be on Saturday the 10th of September. At this event we can once again let people learn about our club and invite them to come to our meetings. It will be a full day, so if you can manage a few hours we would be pleased to see you. Please let Alan or Jerry know if you can come along. The next full meeting of the Hartford Astronomy Group will be on Wednesday the 14th September. At this meeting, Roger O'Brien will give us a talk about the Artemis project to put humankind back on the moon. Like many projects, this one has hit a few snags which have caused delays. Hopefully, by the time of this talk, the project will be closer to launch. Roger will explain what the project is about and give us the latest update. We would like to thank you, the audience, for coming along to these meetings whether at the university or on Zoom. The support that you give to the club is much appreciated and your helpful comments are always welcome. We would also like to thank the University of Hertfordshire for their continued support for our club. We are always made to feel welcome at the Bayfordbury Open Evenings. Their generosity in making this amazing meeting room available to us is sincerely appreciated. And finally, we must thank the committee who worked tirelessly to bring these meetings to you. Many hours are spent in advance to ensure that our meetings run as smoothly as possible. Have a safe journey home, and we look forward to seeing you again in the near future.